Electron configuration describes how electrons are arranged within an atom's orbitals. Electrons are arranged in shells and subshells around the nucleus of an atom. The arrangement follows specific rules based on energy levels. Electrons occupy specific orbitals within shells. These orbitals are grouped into subshells labeled S, P, D, and F. Each type of orbital can hold a specific maximum number of electrons. The Aufbau principle dictates that electrons first fill the lowest energy orbitals before moving to higher energy levels. This creates a specific pattern for filling electron orbitals, shown here by the diagonal arrows. The Pauli exclusion principle states that no two electrons in an atom can have the same set of quantum numbers. This means each orbital can hold a maximum of 2 electrons, and these must have opposite spins. Hund's rule says that electrons will individually occupy each orbital within a subshell before any orbital is doubly occupied. All electrons in singly occupied orbitals will have the same spin. Electron configurations are written using subshell labels. For example, hydrogen has 1 electron in the 1s orbital, written as 1s1. Sodium can be written as 1s, 2s to 2p, 3sn, or using the shorthand noble gas notation as in 3s1. Valence electrons are found in the outermost shell of an atom and determine its chemical properties. Elements in the same group of the periodic table have similar valence electron configurations, which explains their similar chemical behavior. Recent research suggests atoms may have a fractal structure, challenging traditional electron configuration models. For superheavy elements, relativistic effects significantly influence their electron behavior. Meanwhile, advances in computational chemistry are making valence bond theory more viable as an alternative approach. Lewis structures, also known as electron dot diagrams, show the bonding between atoms in a molecule and any lone pairs of electrons. According to the octet rule, atoms tend to gain, lose, or share electrons to achieve a full valence shell with 8 electrons. Hydrogen is an exception, following the duet rule with just 2 electrons. To draw Lewis structures, follow these steps. First, calculate the total number of valence electrons. Second, identify the central atom, usually the least electronegative. Third, draw single bonds between the central atom and surrounding atoms. Fourth, distribute the remaining electrons as lone pairs to satisfy the octet rule. Finally, if the central atom lacks an octet, form multiple bonds. Let's draw CO2 as an example. First, we count the valence electrons. Carbon has 4, and each oxygen has 6, for a total of 16 electrons. Carbon is less electronegative than oxygen, so it becomes our central atom. Next, we draw single bonds between carbon and each oxygen atom using 4 electrons. We now have 12 electrons remaining. We distribute them as lone pairs, placing 3 pairs on each oxygen atom. However, carbon only has 4 electrons, not the 8 it needs for an octet. We convert 2 lone pairs from the oxygens into double bonds with carbon. The final Lewis structure for carbon dioxide shows carbon double bonded to each oxygen atom, with 2 lone pairs remaining on each oxygen. When multiple valid Lewis structures are possible, formal charge helps determine which one is most stable. The formal charge is calculated as the number of valence electrons minus the number of lone pair electrons minus half the number of bonding electrons. Resonance occurs when multiple valid Lewis structures can be drawn for a single molecule. These structures collectively represent the actual electron distribution. For example, the nitrate ion can be drawn with the double bond on any of the 3 oxygens. Lewis structures help predict molecular geometry using VCPR theory, valence shell electron pair repulsion. The arrangement of electron pairs around the central atom determines the 3-dimensional shape of the molecule. Lewis structures show different types of bonds between atoms. Single bonds share 1 pair of electrons. double bonds share 2 pairs, and triple bonds share 3 pairs. As the number of shared electron pairs increases, the bond becomes shorter and stronger. Sodium serves as a straightforward example of electron configuration. With atomic number 11, its electrons are arranged as shown in the orbital notation diagram. Chromium and copper are important exceptions to the Aufbau principle. Instead of following the expected filling order, they adopt configurations with half-filled or fully filled d subshells, which are more stable. When atoms gain or lose electrons, they form ions with different electron configurations. For example, oxygen gains 2 electrons to complete its octet, forming the oxide ion OCA. Atomic size is a key periodic trend that follows predictable patterns. As we move down a group, atoms get larger because we're adding new electron shells. Moving across a period, atoms get smaller as the stronger nuclear charge pulls electrons closer to the nucleus. Electronegativity measures an atom's ability to attract electrons in a bond. This property increases as we move from left to right across a period, as atoms have more protons and fewer shells shielding the nucleus. It decreases as we move down a group, as valence electrons get farther from the nucleus. Lewis structures play a crucial role in drug development. By visualizing the electron arrangement in pharmaceutical compounds, scientists can predict how these molecules will interact with biological targets, helping to design more effective medications.